Okay, so let's see. So we're not gonna go into every detail at least, right? We will cover the bare minimum because I think to appreciate LP spaces, um, i- it's really difficult if you don't know at least a bit about functional analysis. Yeah. So LP spaces, I think the difficulty with dealing with them is that they can't be if you want to deal with a specific property, it's usually difficult, like geometric properties of LP. And if you want to do explicit examples, those are even like worse. Uh, but in general, especially because you're working almost everywhere, I think that's like where a lot of students struggle. You need to keep in mind that you're working almost everywhere. A lot of properties, especially once you start, once you hopefully maybe learn spectral theory, you'll notice that that becomes particularly important. Yeah, yeah. So there's nothing. The only thing that you might not know right now is like LP spaces. If you everything else is gonna be self-contained. Okay. So let's start with it. So as a bit of a like quick recall, because, and you'll notice like people often say functional analysis is like an infinite dimensional linear algebra. And while you need to be careful with that statement, there is some truth to it. A lot of what we're doing is just going to be what happens if we take this linear algebra thing and then ask what happens in infinite dimensions. Like, how can we make sense of it over there, right? So, as a reminder, I'm sure all of you know, just to be complete, people call either linear spaces or vector spaces over a field K. We will be working with R or C generally because if you work with a vector space over a field that lacks the properties that R and C have, specifically the local convexity of R and C, or a space that is maybe a finite field, uh, those are going to be a little bit pathological. So unless stated otherwise, we will be working over R or C. We'll even like mostly focus on R, right? We won't be needing complex field much. Okay. And we have two operations which are addition and scalar multiplication. Okay. These are trivial things. Of course, there's like the whole addition and multiplication have to be associative. Right? Addition has to be associative and commutative. It needs to have an inverse and an identity. And multiplication needs to be comparable with uh, the field multiplication. So if you take alpha plus beta and multiply, that needs to distribute. Everything you need to have like an actual vector space, right? So just in case anyone forget about that, okay. And a vector subspace is just a subspace of X, sorry, a subset of X that is stable for addition and scalar multiplication. Okay. Um, Once again, we remind what a norm is. I'm sure everyone who's done the homework already familiar with that. It satisfies the triangle inequality. It has a homogeneity property, and the only norm, if the norm is zero, then x is zero. This means if x is not zero, the norm is strictly positive. Okay, so that was a quick reminder. Another sort of reminder that maybe people who have done the exam probably have seen that, right? Because uh, where like the usual norms on Rn, right? You have the summation norm, you have the Euclidean norm, and the maximum norm. All of these are norms over Rn, and I guess one may ask at this point is that if you have a norm, you get a topology, right? Because every norm gives rise to open balls. We're gonna see that, and it gives you topology. Um, Basically, people might wonder if the topology that's generated by any of these norms is different. If you've read the exercise 6, maybe you've already like spoiled this for yourself, but essentially what we'll see is that in finite dimensions, the norm topology is unique, meaning that no matter what norm you pick in Rn, you're gonna get a single topology. In infinite dimension, that's a little bit more complicated. Let me see. Wait, Afzal, can you still attend or? Ah, I thought you've needed to disconnect because okay, sure. So this will be recorded, so don't worry if that happens. Okay, and you can of course keep asking me after the lecture. Um, so as a reminder, yeah, no problem. If we take the space of continuous functions, real valued function, usually I'll write this as CAV. I won't write the R. Um, and it should be understood as the space of continuous real valued functions. Okay. Um, then these three norms, these of everyone should be familiar with at this point. This is the L1 norm, the L2 norm, and then there's the supreme norm. These are all norms over X. The main difference between these types of norms and these types of norms is that these generate a single topology. This is not going to be the case for these ones. There's going to be a very significant difference in that only one of these norms is going to make this space complete. The others are going to fail to complete the space essentially. Okay, and in fact, one may predict that if any of these norms don't complete them, you should already have a prediction in your mind on what the completion will be. Which part, Miss? I can explain that again. Oh, I was talking about the space of continuous functions and the norms that you can define on this space, essentially. Yeah. So I was saying that in the finite dimensional case, we're gonna see that there's only one topology you can get, but only one of these three norms is gonna make this space complete, meaning that the space of continuous function, you probably see that in real analysis, is complete with the infinity norm, right? Because uniform convergence. But if you equip this space with any of these two norms, it's not going to be complete. It's going to be, uh, there's going to be Cauchy sequences that don't converge, essentially. The completion, unsurprisingly, is going to be L1 and L2. So you can think of the space of continuous function as uh, lacking. These are not suitable norms for this space, essentially. Okay? So a little bit of terminology. If you have a distance, then if you have a norm that you can get a metric or a distance, right? Which is defined as the distance between 2 points as the norm of x minus y. Okay? What this tells you is that every norm gives rise to a metric space. Okay? The question that asks itself, and I think I mentioned that earlier in some lecture, if you have a distance, can you get a norm? And the answer is that not always, right? So there are going to be metrics. I think the discrete metric is probably the best example. You can test it for yourself, by the way. Try to see if the discrete metric gives rise to a norm. Um, then you can't get a norm from every distance. Okay? You do need a certain two properties essentially for your metric to give a norm. You need it to be homogeneous, meaning that if you multiply both elements by a constant alpha, then you can take that alpha outside and take its scalar value, right? So you can scale any point and your metric will scale appropriately. Okay? The other thing is that it needs to be translated, meaning that if you translate any of your points, the distance shouldn't change. If these two properties are satisfied, then you can define a norm, right? So you can't always define a norm. Okay? And I'll leave the proof to you. I'll even leave the proof that if you can pick any metric uh, where you don't expect it to be a norm, right? Maybe it fails the translation invariant or it fails the homogeneity. This is why the discrete metric fails on this aspect specifically, right? Because you can scale a function, you can scale 2 points by, for example, 5, and the distance between them is going to be 0 or 1. If you multiply them by 5, this is still going to be 0 and 1. So you have something much larger on this end. Okay? Either way, let's talk about the topology. So, as I was saying, every norm gives rise to a topology. And how does that happen? Essentially, if you have a norm, then you can define the ball of center x radius r as the points y that are norm distance r less than r from x. Okay, and similar to a metric space, once you have balls, well, you have a basis, right, for your topology, and you can define open sets to be union of balls. Okay, and these balls usually have very nice properties. Essentially, you can prove that they are convex, essentially, in many cases. Okay, that's why norm-vector spaces are really important, because they have convex balls. Um, in the general case, or in a more general setting, this need not be the case. So you need to talk about local convexity in that case. Wait, am I lagging? Let me see. Or is my voice lagging? I guess. I think I can switch to data for a moment. Wait, just a sec. Okay. Yeah, so it might be internet back. So I was talking about these balls being convex. Actually, I'll leave it as a proof to prove that these are actually convex sets. Even if you have a distance, the balls will still be convex, I think. In the topological vector space, the balls need not to be convex. So you need to distinguish between a locally convex space and one that's not locally convex. If it's locally convex, then it has an open basis, basically, that serve the purpose of a ball, where they are convex sets, right? And that's actually a really important property, because a lot of theorems hinge on the space being locally convex. Even if we won't talk too much about them, at least yet. We will talk about them a bit once we reach the weak topology. Okay? So in this case they are, but in general they don't need to be. In a Nord space they are convex, essentially, because I think you can probably use the triangle inequality just to get the result. Outside of it, in a general setting where you might not have a norm and just a topology that makes addition and scalar multiplication continuous, that might not happen. So don't need to be both. They can be open sets, and those open sets may not be uh, essentially convex, right? Essentially, there can be metrics where the balls are not convex. I think that's the case. Um, although you can usually I forgot which case, but there are cases where you can find a metrizable space where the balls are convex, and I think Cruden proves it in chapter 1 at some point. I'm forgetting the details usually. It's basically telling you in which cases you can expect convexity. Yeah, exactly. And I think that's what you've just said actually is why the dual space of L half is is basically empty. Uh, you can prove it using this fact. But anyway, either way, you can prove that addition and scalar multiplication are actually continuous under this topology, and that the norm itself is gonna be Lipschitz continuous. Okay, so the Lipschitz continuity is because of the reverse triangle inequality, of course, and the continuity of multiplication and scalar multiplication and addition. You can prove it by sequential continuity if you want, because we're working with a metric space essentially. So sequences do work out. Okay, and when we say a space is Banach, this means that we have a Nord space that's complete and dimetric defined by this norm. So every Cauchy sequence is gonna converge. And Banach spaces are incredibly important in any field of analysis, essentially. Right? I think shouldn't be surprised, right? Because that's the first thing you learn when you go into real analysis. R is complete. So it should be no surprise that we care about them outside of R as well. Okay? So once again, we should ask ourselves when two norms generate the same topology, or when two norms are said to be equivalent, right? So basically, if you can find two constants, positive constants a, b, so that a norm 1 is less than norm 2 and less than norm b. This means that it's true for every x. Okay, so here, um, because we're leaving LP spaces a bit, I need you to be careful with the notion of almost everywhere. This equality happens everywhere as of right now, unless we're working with a norm that only works almost everywhere. Uh, you shouldn't make that assumption. So that's why you need to be very careful working with continuous functions versus LP functions. Okay. The significance is that if two norms are equivalent, they're gonna have the same open set, the same Cauchy sequences, and convergence sequences. So a strategy you can often prove is that you can prove one space complete and then try to prove it's equivalent to a norm that you want to prove is complete. That's what we're gonna see that occurrence in the homework, I think. Countable as argument, you don't need to worry about it too much. I think at this point, um, usually we don't really care about them. If you maybe sometimes you're working with epsilon, you can replace it with 1 over n. You can pick a sequence. You don't need to work with nets. I think that's the important thing. Unless you're working outside of a metric space, you don't need to worry about uncountable sequences. You can always work with a countable one. So that's like rarely a problem for sequences themselves. Okay. Either way, even if we don't have like a metric space, or sorry, even if we don't have a Banach space, we can still complete it. Hopefully, at least I think most people here have done Rodin, so you probably have seen the exercise where you complete a space. I think it was the exercise, at least I remember it right. So essentially, any metric space can be embedded in a complete metric space, which we denote as S bar, right? Which consists of taking Cauchy sequences and writing them as equivalent classes, right? Meaning that S is a dense subset of S bar. So if you want to prove something is completed, usually all you need to prove is that it's dense in that space, even if that space is, even if one of the spaces is not a equivalent class and the other is, you only need to prove one of them is dense in the other and that the other space is complete. Okay? So just needs to be like a little bit of care in the difference between S and S bar, because S is not technically a subset of its completion, it's embedded in the completion, right? Because S is a set of elements, while S bar is equivalence classes of those elements. So just a little bit of care there. Usually it's not like too big of a problem, at least. Okay. For example, and this is actually a little bit of spoil. This is gonna be part of something you have to do in the homework, which is that continuous functions are not gonna be complete for the P norms, and their completion by equivalence classes are gonna be actually L1 and L2 spaces. So it suits our intuition that the P norms are actually the best norms on L1, right? Because if you equip that norm on C, it's not complete. So it's not the correct norm for this space. Okay? Either way, we should get into probably like the a property that we've been delaying for a while, which is that LP spaces are actually Banach spaces. Okay? So here's what we're gonna do. We're gonna use a little bit of an indirect argument. We're not gonna do this directly. Okay? So first of all, we're gonna start with P between 1 and infinity. We take f to n to be a Cauchy sequence, and it's enough to show it has at least one subsequence that converge. So this is a powerful tool you need to always be aware of. If a Cauchy sequence has even one subsequence that converges, then that's enough because of the triangle inequality. Okay? Meaning that if a Cauchy sequence doesn't converge, that means it has no convergent subsequences. Okay? So here's what we're gonna do first. First of all, I'll leave that as an exercise. We can extract a subsequence where the difference between any two subsequence terms is less than 1 over 2k. And this is actually not very difficult. You can construct it inductively. Okay? So what we are going to prove essentially is that f and k actually converges in LP. So first of all, we're going to set gm to be the summation from 1 to m of f and k plus 1 to nk. This should be indexed by k, by the way, not I. So k equal 1 to m. Okay. First of all, the norm of G is gonna be less than 1. Obviously, by the way, because you're taking norm here, it's the norm of the summation that's less than summation of the norms for f and k. So it's less than the summation from 1 over 2k, which is less than 1. Okay. This is an increasing sequence. It's positive. Always we're taking absolute values. So the MCT applies. Okay. And this tends to a certain finite limit, which we'll call g of x. Okay. Uh, you're picking essentially for every element in the sequence, you're picking another element. I'm not sure if that counts as full choice. Maybe it's countable choice, but that would be a little bit out of my expertise. But for every nk, you're picking the next term so that the difference is less than 1 over k, and you're doing that infinitely many times. I would assume it's countable choice. Probably not, but you know, you never know. But either way, um, at least for our sake, uh, it could rely on choice. I don't think it relies on choice because it's a bit too. It doesn't strike me as a choicey type of function because you're just picking a subsequence. Yeah, so that works out. Could be, but at this point, like, at least we are full choice enjoyers here. Hopefully, we will actually once we prove there will be actually a theorem that heavily relies on choice coming up in a bit. Either way, let's see here. So just notice that the difference between fr and fm is less than fr. This should be fr plus 1, and then there's dot, and then there's so we're just continuing. So r plus 1, r plus 2, up to n plus 1, up to n, and that's less than there should be a less than here, right? So this is less than g of x minus gm minus 1. So a little bit of a latex issue here. Okay. What this means is that fn of x for a fixed x is Cauchy and converges to f of x. Okay? And this is gonna be our limit essentially. Okay? Um, Either way, we just proved that we just picked a limit f of x, and because f of x minus fn of x is less than g of x almost everywhere, then the f itself is gonna be LP, and it's gonna converge to fn by, for example, the dominated conversions here. Okay? Because G itself is LP, this is gonna be this is just an application of the Lubeck dominated conversions. Okay, let me see what we're talking about. I'm not sure. I hope maybe I'll look into it after the lecture at least because I've never seen too much about the difference between dependent choice and choice and countable choice at least. So I'll have to look that up. But just as a quick reminder, essentially what we did is just pick this GM, which is, and the limit basically acts as a dominating function. So the argument we're trying to prove here, we're trying to prove that the limit of f and k is LP by dominating it, by using the dominate conversions. And that's why we pick GM, because once we go into the difference between fm and fr, it's gonna be less than gm minus gm plus 1. Okay? So because this is a Cauchy sequence in R, which is complete, this is gonna be conversion to a limit f of x, and we're gonna have this estimate almost everywhere. Because this is true, you can just use dominated conversions. F is gonna be LP, and things work out. Okay? For the infinity case, it's a little bit easier in the infinity case actually, because you don't need to do any sort of tricks in that regard. If Fn is Cauchy in L infinity, then the infinity norms already bounds Fn. So we don't need to do like, notice what we have done here by defining g of x was also we can bound fr minus fm of x. So we can prove this is a Cauchy sequence in R. In L infinity, this is automatically true because the infinity norm is already a bound. Okay? And what this means, so notice, yeah, so this is the essential norm. I was about to say, notice that this inequality is almost everywhere. This is not everywhere equality. This means that there is a null set where this is true. Okay, so notice how anytime we're dealing with LP, we need to be a little bit careful about inequalities. Uh, okay, and this means that outside of this null set, we essentially have uniform convergence, right? Because you're bounded by an infinity norm. Okay, so this sequence converges uniformly outside of a null set, and you can find a uniform limit f. Okay, if you want to be a bit more explicit, that's why I added this comment, is that uh, you can just define f to be 0 on n, right? And get the limit in L infinity. So that's basically the proof. This is how Brazis does it, at least. I'm not familiar with other proofs. I could be wrong. I think this is usually the one people default to for proving LP's Banach. Okay, so let's talk about norms. And I think I've mentioned something a little bit offhand earlier, which is that norms on Rn generate a single topology, right? That's what we're gonna try to achieve. And surprisingly, the next section after this is gonna be exactly why this only works for Rn. It's because during proving this, we're gonna use the Heim-Borel theorem. We're gonna use that the closed and bounded the unit ball, the closed unit ball, because it's closed and bounded, it's compact, and that compactness is why we are able to prove that every single norm is equivalent. In infinite dimension, that's never gonna be the case. So it's not just that there's one infinite dimensional space where it happens. We're gonna see that the unit ball being compact classifies finite dimensional spaces essentially. So let's go back to our topic. We're working with finite dimensional spaces, and we need to prove. Basically, our goal is to prove that all norms are equivalent to each other. Okay, so just a reminder, we need to prove that to find two constants so that any two norms have this equality. Because this is a transitive relation, essentially, you only need to prove that all norms are equivalent to a single norm. Okay, and the norm of our choice was the one norm. You could have done it with, some people do it with a Euclidean norm. It's not too much of a difference. Okay, because of Cauchy-Schwarz, of course. So first of all, and people have already seen this type of argument we're gonna do in problem 6, right? There's a b such that norm of x is less than beta norm 1, right? And the reason is that's true is because every x can be represented by summation of x ei xi, where ei is the basis, by the triangle inequality, and taking the maximum of n of xi. Sorry, this should be, yeah, so the maximum of n of xi and norm x, because norm x1 is just sum of actually, wait, sorry, this should be, yeah, so my apologies. This should be EI, and the norm of x is sum of absolute xi. Okay, so a little bit of a mistake there, because the sum of EI was just Bn, so that's not gonna work out. Either way, I'll fix that in a second. This should be EI, and that's norm x. So we prove that the norm x is bounded above by a constant times norm 1. To get the lower bound, essentially, because that's what we need to prove that these are equivalent. We need to get a lower bound on this norm. What we're gonna use is that Sn is compact. Okay? And that's what we're gonna essentially try to do. Because if we restrict n to Sn, it's gonna be continuous, right? And you can just use sequential continuity. It falls directly from it. Okay? Because it's continuous on a compact set, it attains its minimum, which we're gonna call alpha. Okay, alpha is going to be strictly positive. I'll leave you to check why that's true, why it can't be 0. And alpha is less than the norm of x. And okay, for every x in Sn. Specifically, if you take x over norm x1, this is in Sn. Because remember, we're working with Sn with the one norm, with norm x1. Okay? So if x is not in Sn, you can just take x over norm x, basically normalize it. And by this inequality, we get that n of x is greater than alpha norm x. So we got our lower bound, essentially. Okay? Hopefully this argument makes sense. I'm not sure if I explained it too well, but essentially we're trying to get a upper bound beta alpha and a lower bound alpha norm x1. The lower bound we basically got from proving that norm restricted to Sn is continuous. So it has a minimum. Okay? It has a minimum on x of Sn. And then we just take a specific x, which is x over norm x1. And this works for any x. Okay? Because this norm was arbitrary, we proved that an essential what we have proved here is that an arbitrary norm is equivalent to the one norm. So all norms are gonna be equivalent. Okay? It's actually a very simple argument if you think about it for such a strong fact. The saving grace is just that Sn is compact, which doesn't always need to be true. Yeah, so problem 6, I think I've seen some interesting ways to do it, but it's essentially just relying on the transformation formula at least. Let's see. And just as a remark, if there's two ways to prove that this is true for any finite dimensional vector space, not just Rn. Either one, you admit that the Hahn-Burrell is true in finite dimensions. Maybe you have already seen the proof of that. If you have seen the proof of that, then you can just do the exact same argument here. If you haven't seen that, then what you can do is define a function from Rn to your space, which is finite dimensional, that takes x1 to xn to f of x, which is sum of xi ei, where ei is the basis for x. And this map is gonna be a linear isomorphism. So it's gonna be, because it's a linear isomorphism, it's gonna be a homeomorphism because of continuity on finite dimensional spaces. Every linear map is continuous on finite dimension, essentially. So the topology here is equivalent to the topology here. So because there's only one topology on Rn, there can only be one topology on X, norm x1. Either way, the finite dimensional spaces only have one vector topology. You can't have more. And this is actually uh, why in finite dimensions there's essentially no there's no functional analysis to be studied. So let me see. Mm-hmm. Sure. Yeah. So that's kind of the argument we did. Okay. So as I was saying, the reason why finite dimensional spaces are so nice is because the unit ball is compact. Okay? But a lot of interesting theorems in infinite dimensional spaces uh, basically fail in that regard. So you don't have compactness of the unit ball. That's why in a maybe in I think next lecture or probably the one after that, but probably next lecture, we're gonna define a weaker topology just so we can get a sort of compact ball essentially. Uh, Unsurprisingly, the weaker topology might not be normable or even metrizable, but at the very least, we will recover these compactness results in a weaker topology, and then we'll think, okay, how can we upgrade these results from the weaker topology to the actual norm topology? Okay. Um, but as for now, I think this is the main reason why people even bother with the weak topologies, why even people choose to have different topologies. It's because you just lose compactness completely in infinite dimensions. Okay, so here's what we're gonna do. We're gonna prove a lemma, and this lemma is gonna help us prove that the unit ball in infinite dimension is never compact. In fact, the unit ball is only compact when the space is finite dimensional. Okay, so if Y is a closed proper subspace, then for every epsilon in 0, 1, you can find a vector x so that x is a basically unit vector, and the distance between x and y, remember this is the infimum between the distance between x and y, where y is in big Y, is greater than 1 minus epsilon. For simplicity, you can for example, you can take epsilon to be half, so the distance between these are greater than half. Okay? And just as a remark, in a metric space, X belongs to the closure if and only if the distance between X and A is 0. Okay? Outside of the metric, this would only be true in metric spaces because you would be able to find a sequence essentially. That's why in metric spaces sequences are enough. Okay, so X is an A bar means you can find a sequence in A that converges to X. Essentially, we're trying to prove that the distance between X and Y can be made to be greater than a fixed value. What we're gonna do is use this fact to build a Cauchy sequence. We're gonna keep building sequences where the distance between X and all of the previous terms is greater than 1 minus epsilon. Okay, so yeah, there is a difference that, well, actually no, if you can pick any epsilon between 0 and 1, it would still work out. You just need this to be greater than 0, essentially. So any number between 0 and 1 would work. Yeah, so that's actually true. There should be a space. So theorem's infinite dimensional spaces rest on the fact that the closed unit ball is compact. This would not work in infinite dimension. Infinite dimension, we definitely we definitely don't have compactness. We do have compactness, but in a weaker form. Okay. Yeah, it's actually very easy to see to miss essentially. But essentially, infinite dimensional spaces, uh, we basically found a way to compromise. We found a way to recover compactness. Uh, but as of right now, we need to prove that we did actually lose compactness. So let's prove this property. And the proof is a little bit technical, but it's not difficult, at least. So because Y is a closed proper subspace, just pick an element in its complement. Okay? Because Y is closed, the distance between Y and the big space Y is gonna be alpha, which is greater than 0 by our characterization here, right? And because 1 minus epsilon is less than 1, then we have, that's why we need to be less than 1. We have the inequality alpha is less than alpha over 1 minus epsilon, right? Because this is a number that's less than 1, so this is bigger. Okay? Then because this alpha is the infimum of the distance between Y and big Y, the infimum tells us that we can find an m0 in Y so that Y minus m0 is greater than alpha 1 minus epsilon, right? Because this is not a lower bound. So we can find something that's smaller than it, but at least bigger than alpha. You're basically just squeezing this element in. Okay? If we set x to be y minus m0 over norm y minus m0, this is a unit vector, right? Because the norm is equal to 1. And for every m and y, so all we need to prove right now is that the distance between x and y is greater than 1 minus epsilon. Notice that x minus m is just y minus m0 over norm minus m. We just take y minus m0 inverse and common, essentially, right? So we remove it from here, and that's why we need to multiply by it here, okay? So that we are left with y minus m0 minus norm y minus m0 norm m. So this is like a very simple trick that you can use essentially, which is that you're just multiplying by y minus m0 times y minus m0 inverse. I'm sure you've seen that a million times already. So by the way, these are two separate norms, so that doesn't look like a single norm. No, actually, this is correct. So this is norm y minus m0, and this is just the end of this norm. Should have used a different, maybe a bracket here. Either way, notice that this element right here, which is m0 minus m times constant, these are in y, right? Because m is in y, m0 is in y. So this is a scalar. So this element right here is in y, and this is in y. Because y is a subspace, this whole thing right here is in y, right? And remember, alpha is the infimum of the distance between y and any element in y, big Y, right? So that's why this term is bigger than alpha. Okay, so we're just doing a little bit of a technical trick here, right? And because of how we chose, because of this estimate right here, this is bigger than 1 minus epsilon, and we're basically done. We proved that x is our element. Okay, so if you're still not convinced, you should write it. If you try to write this down, I'm sure it'll only take you a couple of minutes. It's not particularly profound. Okay, there's just a little bit of trick you can get used to. So now, equipped with this knowledge, we're gonna prove that if x, we're gonna prove Rice's theorem essentially, not to be confused with Rice representation theorem, of which there are quite a few actually. But essentially, if x is a normed vector space, the closed unit ball is compact if and only if the vector space has finite dimension. Okay, and here's what we're gonna do. We're gonna construct this essentially explicitly, or I should say inductively. Let's say we picked our first element. It doesn't matter which element it is, and we've constructed up to n minus one. So we're supposed that we've constructed this sequence up to n minus one, and if we prove this is true, then you basically start from y1, you construct y2, and so on. So once we have chosen up to n minus one, we call yn the linear space that's spanned by them, right? So hopefully people remember the linear algebra. You take the y1 to yn minus 1, you take all linear combination, and that's going to be a linear subspace of dimension n minus 1. Okay? And that's what we're going to do. Because yn is going to be finite dimensional, dimension specifically n minus 1, it's going to be closed. And I'll leave to you the proof why every finite dimensional subspace is actually a closed subspace. Okay? It's not too difficult. It's not trivial either. I'm sure you guys can figure it out. Okay? So if yn is finite dimensional, it's gonna be closed. And x is infinite dimensional. So yn has to be a proper subspace. Okay? Because it's a proper subspace, our lemma can be applicable, right? We can find a term yn such that norm of yn is equal to 1, and the distance between yn and y is greater than 1 minus epsilon. Notice that what this means is that the distance between yn and any other term that comes before it is greater than 1 minus epsilon for some fixed epsilon. What we have just proved is that the sequence we have constructed here, that we can essentially construct to infinity, you may ask whether that requires dependent choice. What matters is that we have a sequence where the distance between any two distinct elements is greater than 1 minus epsilon for some fixed epsilon. So no subsequence can form a Cauchy sequence, because any subsequence you take is going to have the same issue. It's not going to be Cauchy. Okay? And because all of these are going to belong to the unit ball by how we constructed them, it follows that this set is not compact because it's not sequentially compact. And in metric spaces, sequential compactness and compactness are equivalent, essentially. Okay? I guess. Well, it just means that you can't have a finite linear subset, essentially. Or I should say, you can have an infinite linear. You can keep adding more elements that are not a linear combination of each other. But either way, we've just this is the most important theorem on why people in infinite dimensions they opt to work with a weaker topology, because compactness is incredibly important, and you really don't want to lose on that. Okay, so let's move to the second part. This is gonna be a little bit shorter, so I would say we've pretty much done the heart of normed spaces essentially. Okay. Of course, I should mention that normed spaces are by no means the end of the story. There's a lot of interesting vector topologies that are not normed. They're topological vector spaces, but we're not going to touch on that too much. Okay? So now we're going to talk about linear functionals and the dual space. Okay? And these are going to be basically the most important way to study a space is going to be revealed to be by studying its dual space. The Hahn-banach is going to be a theorem we're going to see soon, is a first encounter of why the dual space reflects the space itself. Okay, so let's talk about that. First of all, I really shouldn't be defining these, but as a reminder, a linear map is just a map that respects the vector space structure. So it's distributive over addition and scalar multiplication. You can call it the, I think in categories here, the morphism of vector spaces. Uh, I think so, at least. Either way, continuity is the, as you would expect it to be, for every epsilon, you can find a neighborhood delta of x so that any point in that neighborhood implies the f of distance between f of x and f of a is less than epsilon. Uniform continuity forces more so that a single delta have to suffice for any x and y uh, in the space. So you can't pick for every epsilon one delta. A single delta need to work for all the points. Okay. As a recall, Lipschitz continuity just means the norm of x minus y is less than k and norm of x minus y for some positive k, and f is a contraction if k is between 0 and 1 strictly. Should really emphasize that, okay? Yeah, so k holder continuity just means that you have some alpha here, so this might be, you might ask for something stronger, right? So notice you're asking for the distance between x and y. If you ask this to be strictly bounded by nor x minus y square, you're forcing a stronger form of continuity on your space because you're basically asking it to be even stronger than Lipschitz continuity. So that's what holder continuity means. You're just raising this to the power of alpha. Um, as a reminder, can someone remind me why we even care about 0.5? I really need to know if people know about this theorem. Why do people care about contractions? There's a very classical result that's, um, yeah, so the contraction principle is probably why we even bother with contractions. Basically, if you prove something as a contraction, it has a fixed point that can be used, for example, in solving ODEs. If you have an ordinary differential equation and you can write that equation as a sort of operator that you can prove is a contraction, you can prove that that differential equation has a unique solution through the contraction. Okay. Lastly, we say f is an isometry if it preserves the distance, essentially, where the norm of x is the same as norm of f of x. Isometries are going to play a really important role once we reach Hilbert spaces. A very important theorem tells you that separable Hilbert spaces are isometrically isomorphic to little L2, which we're going to see when we do Hilbert spaces. Yeah, so isometry just means it's a distance preserving function, essentially. Okay? So there's a general philosophy you can follow in linear spaces or vector spaces, which is that if you have a property that works locally at some point, if you have any property that works locally, and that property can be translated through your space, then you should expect it to hold everywhere. This doesn't. This is not just about like North spaces specifically. In any vector space with a topology, uh, you should really think if you need to prove something globally right away. Morphism. Okay, so that would be an isometry. Let's say maybe. But either way, um, I'm not sure. The first time I saw this theorem, um, I was essentially extremely surprised. But it's gonna seem to be a very natural theorem, which is that if you have a linear function, these four statements are gonna be equivalent. Which is that if function is continuous at 0, it's continuous everywhere, it's uniformly continuous, and it's bounded. So that's why in people usually don't say continuous operators; they would say bounded operators, and you should understand that these are equivalent in North spaces. In non-metrizable spaces, continuity is stronger, but you don't need to worry about that yet, at least. Okay. So in our case, because we are in a metrizable case, continuity and boundedness are equivalent. Okay. So let's prove that continuity at 0 implies continuity everywhere. So And we're going to do this arbitrarily. First of all, the reverse implications are all trivial because this implies the function is Lipschitz, which means it's going to be uniformly continuous, continuous, and continuous at 0. So we just need to prove that 1 implies 2, implies 3, implies 4. Okay? So 1 tells us that we have continuity at 0. We just need to write down what that means, and an idea should come in mind. Okay? For every epsilon, we have a delta such that if norm x is less than delta, norm f of x is less than epsilon. Why? Because f of 0 is 0, right? That's the first property of linear function. Uh, the image of 0 is 0. Okay? So that's why f of x is alone here. Okay? Now, if we just replace x with x minus a for any a in x, we're just going to get continuity. Because now we have x minus a is less than delta, and here we're going to have f of x minus a. Because f is linear, that's just going to be f of x minus f of a. So we just established continuity. In fact, we can do the same thing with x minus y. Because this works for any x, we can just replace it with x minus y. And so once again, we have for every epsilon, there's delta, x minus y is less than delta, f of x minus f of y is less than epsilon. We just got to uniform continuity. With the only assumption we have made so far is that f is continuous at 0, and we've already have uniform continuity everywhere. That's why like linear maps are incredibly beautiful in how they work. Like often you can, if you prove something locally, it just works everywhere as long as it moves by linearity. So that's why people often normalize while they work in North spaces. That's why we have seen actually an example on how this works in proving Minkowski, right? The first thing we have done is prove that we can afford to work on the unit sphere. So you should always have that in mind when working in North spaces. Okay? Either way, it remains to show that uniform continuity implies boundedness. And we're going to argue by contradiction. So let's argue that um, L is not a bounded operator. So what's the converse of this theorem is that for every m, you can find at least one x where L of x is strictly greater than mx. This allows us to pick a sequence. Because this works for any m, you can replace m with for example, n, or 1 over n, okay? And for every n, we can pick a sequence xn. So that's why we are able to pick a sequence so that L of xn is strictly greater than n norm of x, okay? Clearly, xn is not 0, because if n is 0, then this is going to be 0, this is going to be 0. You get a contradiction that 0 is strictly greater than 0. Okay? This is why we can define this sequence, divide by xn. Okay? If we take un to be xn over n norm of xn, then un converges to 0, right? Because norm of un is just 1 over n, that converges to 0. Okay? But notice that L of un is just L of xn over n norm of xn, which is greater than 1, which means that the limit of norm of L of x un is greater than 1. But that's a contradiction. Can someone tell me why this is a contradiction? Keeping in mind working in North spaces. So we picked we were able to find a sequence that converges to 0, but the limit of norm L of un is greater than 1. Well, why is that a problem? I should remind actually, we are assuming uniform continuity. In fact, I will give a hint. We only need to assume continuity to get a contradiction here. So anyone has an idea? Maybe something about continuity that works in metric spaces? Yeah. So un converts to 0. But if we take L of un, because of our assumption, we have that this is greater than 1. Why is this a problem, essentially? All right. Why is this a contradiction? Right? So we started by assuming that it's not bounded. Yeah, kind of, but I think in general, in metric spaces, what's one characterization of continuity? Like if I say f is continuous at 0, what's one way to look at it? I don't need to look at this. Like, how can I interpret that in terms of sequences? Yeah. What's the image of L of un? It's L of 0, right? And L of 0, do you see the problem? Yeah. So we assume that un converts to 0, but L of un does not converge to L of 0, because this is greater than 1, right? So we contradicted continuity at 0, essentially. Do you see the problem? Essentially, we were able to find a sequence that converges to 0, but L of un does not converge to L of 0. Yeah, and so that's the contradiction here. Okay? We started by assuming continuity. We reached that L is not continuous. Okay? Let's see. So actually, motivated by this definition, so notice that so far, what we have proved is that norm Lx over norm x, as long as we assume x is not 0, is bounded by some constant. This motivates the definition of the norm of L to be this least upper bound on norm Lx over norm x, where x is not 0 and x is in x. Okay, so if we have L from x to y, it's a linear function. Then if L is continuous, this is gonna be its norm, which is well defined, by the way. It's gonna exist because uh, it. So I should actually give an important remark here. This, even though it exists, it doesn't need to be achieved. So you can have the norm of L in a way where no point in your space uh, is equal to the norm of L. It's not always true. Bounded at infinity. So they can't be bounded at infinity. Because if they're continuous, they have to be bounded by some constant. A fixed constant. This can't be infinity. That's what you're asking. So norm of L is a real number, essentially. Okay? And if a function is continuous, we're just gonna call it a bounded linear operator. Okay? So that's why people in norm spaces, we're just gonna say bounded linear operators because those are the one we care about. Okay? And the space of continuous function from x to y is gonna be called little l x y, not to be confused with the space of measurable functions, because I think we used a similar notation. Okay? If we have the same space, this should be big Y, of course, and this should be big Y. If the spaces are equal, then we just say L of x. Okay? Um, so of course we sort of skipped a step here, which is that how to make sure that this is an actual norm, right? And that's what we're gonna prove. So if norm of L is 0, this means that the supremum of norm Lx over norm x is equal to 0. Okay? Yeah. So I think that's like a fair mistake that I have done myself. So when we say L of xy, we mean bounded linear functions, essentially. Yeah. So in finite dimension, the reason why this is not a problem, because linear functions are, of course, they're always continuous. That's what we proved. And infinite dimension, you need to be a bit more careful about that. Okay. So let's actually prove that this is a norm. If norm L is 0, then for any x, norm of Lx is also less than 0, because by the definition of the norm. Okay, this means L of x is 0 for all x, and we just proved that L is 0. So the first property is true. For the second property, if alpha is in K, this is R or C, then norm of alpha x is alpha norm of Lx. Because of how we defined L, we have that norm Lx is less than norm L times norm x. Okay, so this is always true. So that's where we get that norm Lx is less than norm L norm x. Okay, and if we take the supremum on this side, basically by dividing by x and taking the supremum, we get that norm alpha L is less than absolute alpha L. Okay, so we proved one direction. The other direction is that for every epsilon, we can find a x epsilon so that alpha L x epsilon, which is alpha absolute alpha Lx, is greater than alpha norm L minus epsilon norm x. This is by definition of the supremum, essentially. Because alpha norm L is the supremum, we're able to make this choice. Okay? And what that means is that for every epsilon, we have that this quantity, once again, we divide by x epsilon, we take the supremum, we get norm of alpha L by the definition of the norm. Okay? As a reminder, norm L is the supremum of Lx over x. Okay? So if you want, you can redo this calculation to be convinced of what we're doing here. Okay? But because we proved this for every epsilon, we proved that norm alpha norm L is less than alpha L, so we proved the homogeneity of the norm by these two inequalities. Okay? The triangle inequality follows in a similar fashion too. L1 plus L2 of x, that's less than L1 of x plus L2 of x by linearity, by the triangle inequality. Each one of these is less than their respective norm times norm x, once again, by the definition of the norm. By the way, sorry, this should be uh, outside here, not here. So this is not norm L2, this is norm L2 of x, okay? And once again, we divide by x, we take the supremum, we get that norm L1 plus L2 is less than norm L1 plus norm L2. So this is an actual norm on our space, okay? Finally, and probably like the cornerstone of why the theory of duality even makes sense. I'm not gonna prove this actually because I think that these technical details you probably have already seen in a reanalysis course, improving continuity of C0x. They're not incredibly different, right? So we don't need to waste too much time on them. Um, I'll leave a certain similar type of proof in the homework. But essentially, the remarkable thing about the space of continuous linear functions is that if the range is continuous, that's enough to ensure the continuity of the space. No matter what x is, x doesn't need to be a complete space. It can be any arbitrary normed space. Okay? So if y is Banach, then the space Lxy is also Banach. And I'm gonna give like a little bit of a sketch of an argument. That's usually how that's similar to how we proved LP is Banach essentially, which is that if Ln is Cauchy, then you can use that to prove Ln of x is Cauchy. Compare that to how we proved L infinity is a Banach space. You'll find that it's the exact same type of argument we have done. Okay? Because it's Cauchy in y, it's going to be conversion to some limit L. Because you found your limit, all you need to prove that this is an actual linear continuous function. You just need to work a bit with triangle inequalities, a little bit of estimates. It's not too difficult. And then you need to prove that Ln converges to L in L of xy by the definition of the norm. Okay? So again, I'll leave the details of this argument. This is a classical type of argument to prove something is a Banach space. Usually proving a Banach space is it's usually not incredibly difficult, and there are certain cases where you need to be a little bit clever, like in like how we proved LP is Banach, right? For the most case, a lot of the future ways people prove something is Banach uh, relies directly on them being a subset of a Banach space essentially, because usually if you prove something is Banach and it has a closed subset, so a closed subspace, then that subspace is also going to be a Banach space. I can verify why that's the case essentially. So that's like one way you can prove something is a Banach space. You only need to prove it's a closed subspace of the Banach space. But either way, one important example on when we're gonna use this is when y is gonna be r. Okay, so there's two types of dual. There's a algebraic type of dual, which you may have seen in linear algebra perhaps, and there's the dual that we're gonna be dealing with, which is the topological dual space. Okay, so if X is a normed vector space, then the continuous functions the space of continuous function from x to r of linear functions, we're gonna call them linear functionals actually. And the space of linear functionals is gonna be called the dual space of x. Okay? And because R is Banach, so is the dual space. So that's why this theorem is so important. Okay? Um, but as we will see like very soon, the study of a space itself is gonna be directly reflected in this dual space. That's why people really care about dual spaces, because a lot of the facts you need to know about your space itself can be studied by studying the dual space itself. Okay? Of course, this has the norm topology of L. We need to soon in the future we'll need to be able to distinguish between different topologies, because we're gonna stop working with a single topology on our space. We need to deal with uh, essentially multiple topologies. On the dual space specifically, you need to distinguish between three types of topology. You need to distinguish between the weak topology, the norm topology, and the strong topology. All of them are gonna be related in some way. Okay. Just a little bit of a notation that makes life easier. We say we write this inner product Lx to mean L of x when L is in x star and x is in x. You may ask why this is written an inner product. There is an actual reason, which I'm not gonna go into like right now. Okay. It's basically related. I think you can find a little bit more about the details of duality in chapter 4 of Ridden if you're interested in that regard. But they do work in topological vector spaces, I think. Um, either way, we need to we need to ask ourselves a crucial question here: is that how do we know that this space is interesting enough? Because looking at it, um, it is possible that this space is maybe finite, maybe it's not very interesting, maybe it's too messy for our liking. Why do we even care about the space? Um, and that's where like the next theorem that we're gonna discuss is gonna come into play. There's gonna be a theorem that ensures that no matter what, we always have a sufficient duality theory, essentially. Okay, and that's gonna be the last section of our lecture, which is the Hahn-banach theorem. So, as a little bit of a remark, the Hahn-banach is the it's I think people call it the fourth cornerstone of functional analysis. I'm not sure if there's an order. There's basically four theorems in functional analysis that are called the four cornerstones of functional analysis. There's the uniform boundedness principle, there's the open mapping theorem, the closed graph theorem, and the Hahn-banach. The Hahn-banach is one name to many theorems. There's the Hahn-banach extension theorem, there's the analytic form, there's the geometric form, there's the separation, there's strong separation. There's a lot of Hahn-banach theorems, which we won't discuss all of them. For our sake, we're gonna only need the analytic form. If we do need the geometric form, I'll come back to it at least at some point, which is also like an incredibly important theorem. For what we are trying to do, it's a little bit on overkill for a measure theory course. Okay, so the Hahn-banach is also in a family of theorems that people call axiom of choice type of theorems. So they're theorem where you have an existence, but but you have no idea what the fuck it looks like, and that's gonna be reflected in the proof where we're gonna use an equivalent form of choice. An interesting fact about the Hahn-banach is that it's actually weaker than choice. So the main type of argument that we're gonna use here, I think it's fitting that Martin is here. You were the one that asked me about the induction, right? You told me, I think at some point you asked me about transfinite induction, right? So that's like the first time, I think, at least I think this is the first time we're gonna use transfinite induction. What we're gonna do is show that induction itself is not enough. We need to upgrade that inductive argument. So, first of all, the analytic Hahn-banach starts with a dominating function. First of all, if you have a function that is basically, you can call it positive real linear, where p of alpha x equal alpha p of x for every x and every alpha positive, and it works as a norm essentially. So notice that we're sort of hinting that P can be a norm itself. And that's going to play a very important role uh, very soon after when we're trying to relate basically elements of the space to linear functions. Okay? So it's sub-additive. But essentially, if G is a linear subspace, and we have a function defined on the subspace that's dominated by P, we can find a certain extension to the whole of space X that extends G and it remains dominated by P. So we've gained two things here. One thing, we had a function that's defined on a subspace extend to a function that's defined on the whole space. That's one thing. Two, how do we ensure that if G is, for example, continuous, right? What if G is bounded by a certain constant that makes sure it's a bounded operator? Can we make sure that the extension is also bounded? That's where the P plays a role in the theorem. It tells you that if G is, for example, a bounded operator, you can extend it to a bounded operator. It also tells you that if you can replace P by a norm of X, perhaps you can find a function, an extension f, that has the same norm as the norm of X. Okay? So here's what we're gonna do essentially in the proof before I go into details. I'm not gonna focus too much on the details, even though I wrote them. I just need to uh, tell you when to think about these types of arguments. So let's say, for example, we have a function defined on a one-dimensional space, and I want to extend it to 2 dimensions. Okay? So let's say I have a dimensional space G, and I take an element outside of G and I define G plus or X0, right? So that's a 2-dimensional space. And then I do a certain explicit argument and I prove that I can define this extension. So I can move from 1 dimension to 2. Because of how induction works, this tells you that you can basically keep extending G up to dimension n. But we're working with X here. That's infinite dimensional. So induction only can let you go up to a finite amount of extensions. How do you push that boundary? How do you prove that you can extend that to infinity? That's where transfinite induction comes in. Anytime you think to yourself, man, I wish I can apply induction up to infinity, then you should probably think that the transfinite induction is the right play to do. Okay? So that's what we're gonna do. Exactly, that's exactly what we're gonna do. We're gonna prove that we can extend G by 1 dimension, and then we're gonna use transfinite induction. Okay? So let's start with the extension by 1 dimension. Okay, I'm not going to focus too much on details. They're not incredibly difficult. Um, they might be difficult to think about if you're doing this for the first time, but following is not extremely difficult. If G is not equal to X, just pick an element in its complement and define G1 to be X plus Tx1. So you can think of G1 as extending the dimension of G by 1, right? By taking X1 and then adding every element in G, Tx1, okay? So you've raised the dimension by 1. You define h of x plus tx0 to be f of x plus t alpha. And alpha, because remember, we're trying to bound our function by a p of x. So let's say we're trying to bound h of x plus tx0 for a moment. We want to be able to bound it by p of x plus tx0 because that's the goal of the extension, right? We want the extension to be bounded by p of x for every x in x. Okay? So this is what we want to achieve if h is going to be our extension. Okay? And notice it is going to be our extension because if an element is in G, then t is equal to 0 and h and f agree. Okay? How do you ensure that this is actually true? Okay? Think about it. We want f of x plus t alpha to be less than p of x plus tx0. And that's essentially how we're gonna pick alpha. We're gonna pick alpha so that this is true. Okay? First of all, because of the first property, we don't need to worry about the t itself. We can divide by t and we can normalize x. So we can replace x with y equal t of x. Okay? And because of that, we can pretend that t is equal to 1 by removing it essentially. Okay? So what we need to check is that f of y plus alpha is less than P of y plus x0. Okay? And f of y minus alpha is less than P of y minus x0. Okay? We need to study two cases here. Okay? So what do we need? We need essentially alpha. If we remove it here, alpha is an upper bound for this quantity. We need alpha to be between the supremum of this quantity and less than the infimum of this quantity if you take f of y to this direction. Okay? This alpha will exist pretty much from the semi-linearity of the p of x, right? Because f of x plus y, it's less than p of x plus y. That's by assumption on our initial function f, right? And that's less than p of x plus x0 plus p of x minus x0. Here we use the other property of p, right? And essentially all you need to do right now is just uh, move f of y to this direction, then move p of x minus x0 to this direction. Okay? Either way, this means that h will extend f to g1 and it's gonna be bounded by p. So we prove that we can extend any function on a subspace by one dimension. Now we need to use transfinite induction. I personally use the Hausdorff maximal principle. Some people use Zorn's lemma. If you're crazy, you might basically any form of transfinite induction can work here, even if you are like hoping to use something like Tychonoff, for example, for whatever reason, you might be able to build an actual argument from it. Okay, so that's what we're gonna do. We're gonna impose a partial relation on our space and then take the maximal element in that partial relation. That maximal element is gonna exist by transfinite induction, and that element is gonna be what we're gonna use. Yeah, sure. Just doing it directly. Technically speaking, all of them should be viable. It's just a matter of which one is easier. I think the two main tools people use are Hausdorff maximal principle, which tells you that you have a maximal totally ordered subset, or Zorn's lemma, which tells you that if every chain is bounded, then you can find a maximal sort of element. Okay? So the natural order, partial order that we're gonna impose is gonna be, first of all, we take P to be the set that contains all pairs of G star, F star, where G is a subspace and F star is the extension of F. So G is a subspace of G star. Okay, so we take any two pairs where G star contains G and F star extends F. Okay, so one such example would be H, which G1 with H. So G1 with H would be an element of that space because it does satisfy this, right? G1 contains G and H extends F. Okay, so we take all possible pairs, right? Specifically, F star agrees with F on G, and F star is less than P of X for every X in G star. Okay? It should be G star, by the way. So we partially ordered P by setting two elements to be less than each other if G1 is subset of G2 and F2 extends F1. So this is an actual partial order. You can check the properties. I'm not going to waste too much time on these. Uh, Because we have a partial order, the Hausdorff maximality principle tells us there exists a maximal totally ordered subcollection of P. Okay? So because we have this totally ordered subcollection, if we take the union of all M prime, uh, just a second, this should be G star, by the way, sorry. If we take the union of all the subspaces that are in this totally ordered collection, then that subspace, first of all, is gonna be maximal in the sense that you can't extend beyond it. Okay? And you're gonna have to each subspace a function. So how do you define your function on the whole space? Maybe I should write that down actually to make more sense of it. So what you took is you have a maximal totally ordered subset of extension, right? And this is maximal. Okay? You can prove that it is actually infinite, right? So G1 then you have up to Gn, Fn star, let's say, and you can keep going forever. You take all of these spaces, G1, Gn, ultra infinity, and you put them in one big set, okay, which we're just gonna call G star. So let's just call this G1. So you take the union and you call that G star, okay? So we have this from 1 till n of G1, sorry, Gi. That's gonna be called G star, okay? And how do you find a function on G star? Well, it's simple. You just defined lambda of x. If x belongs to G star, it's gonna belong to at least one of these, right? At least one Gn. By the way, this does need to be finite. It's gonna belong to at least one of them. So let's say it's in Gi. So just define this to be fi of x. Okay? So that's how you can define a function on the union. Okay? So that's what we did here. We defined a function on the biggest element on G star. Okay? Where f star occurs on the pair G star f star. Okay? And the rest is just basically just a little bit of computation. You can easily check that lambda is gonna be the actual extension, and it's gonna be the extension to the whole space. Because if lambda hasn't been extended to the whole space, you can just do what we did here. You take an element that's in the complement of G star, and then you can extend lambda by one dimension. Once again, you contradict that G star is a maximal set. Okay? So this is a classical type of transfinite induction argument where um, you build a partial relation depending on which type of situation you're in. You get this maximal element, and then you prove that it is an actual maximal element, meaning that if it's not maximal, you get a contradiction. You'll see that in any type of situation where you use transfinite induction, you will see this type of argument. Okay? So we proved the Hahn-banach. So we're almost done, by the way. There's just 2 pages left. We're just going to talk about a little bit of its application. I think the first one I've already mentioned, which is that if G is a continuous linear functional, or I should say a bounded linear functional, then you can find a function f that's also bounded. This is because of the p that we have chosen, and this extends G. Okay, which means that if G is a bounded function on a subspace, you can extend it to a bounded function on the dual space. So that's one situation where the dual space is guaranteed to have enough function for our theory. Okay, and you can just use the Hahn-banach with this function, which is norm of G times norm of X, right? So f of x, the norm of f of x is gonna be bounded by, f of x is gonna be bounded by p of x, and that's gonna be bounded by norm G norm X. If you can normalize X, then the norm of f is gonna be bounded by norm of G. Okay. Another situation where, as I was mentioning, the behavior of the elements is reflected in a dual space. Every element has a f0 and x star. This doesn't need to be unique, by the way, such that norm of f0 is equal to norm x0. And f0 x0, remember this means f0 applied to x0 is equal to norm x0 squared. Okay, so I think in LP this is gonna be unique. So you can find a unique LP, a unique element in the dual space where this is true. Generally, this is not true. You need a stronger structure on your dual space to guarantee that this is a unique element. Okay, and you can basically just use the corollary that we just mentioned, where G is R of x0, G of tx0 is tx0, meaning that norm of G is equal to norm of x0. Okay, and you just have the exact same result. So norm of f is gonna extend the G, and norm of f is gonna be equal to norm of G, which is norm of x0. Okay. Finally, this is occurrence number 2 of the elements are reflected in their dual. If you have x and x, then the norm of x is the supremum of f applied to x, where f is in the dual space of norm less than 1. So if you need to compute the norm of an element, and remember, x can be any norm space. It can be LP spaces. It can be spaces where functions are really difficult to deal with. Sometimes you can use the duality. in order to compute that. And that can even help in theory sometimes. Okay? So first of all, we can assume x is not equal to 0, because if x is 0, then all of these are 0, and we are done. Okay? By the definition of our norm, we're gonna have f of x. Sorry, give me a sec. Okay, so let's just finish the argument. So because of our norm, right? Because remember, this is just f of x, and this is the norm essentially at this point. The way we define norm of x, remember, it's the supremum of f of x over x. Okay? So the supremum of this value is bounded by norm x, right? Because we assume norm f is less than 1. On the other hand, because we are able to find f0, where the norm of f0 equal to norm of x, if we pick our function to be f0 over x, then norm of f1 is going to be less than 1. It's going to belong to x star, and f1 applied to x, which is just